Hey everyone, today we're going to talk about topic 12.1, the interaction of matter with radiation. There's actually several subjects in this topic, and we're going to start out by going to what I would consider the very beginning. We're going to talk about Max Planck. There we go, Max Planck. And how he basically, I believe, is the father of quantum theory. Now, this lecture is going to be broken up into two parts. We'll do one today, and then the next one will come along afterwards, because there's just so much material in this. I don't want to overwhelm you and give you plenty of time to digest what you've learned. But let's talk about Max Planck and what he observed. This chart here is called a black body diagram. We talked about these in SL a little bit, so just to go over it again with you to remind you what it is. You have two axes. You have the x-axis, which is the wavelength of light that's coming off, and you see it goes from 0 until it goes out to infinity. And then you have the intensity of that light, and the intensity is basically just the power, or how much energy that star is putting out per second. In this case, a star. Stars are very good, perfect light emitters, so they make really good black body diagrams. All right, so they're looking at different wavelengths of light, different frequencies. When they make these light curves here, notice that they kind of make sense for the most part. It's an exponential distribution. Excuse me. As the wavelengths get shorter, the frequency increases. And with the increase in frequency comes an increase in energy, and that means an increase in intensity. And it does that at an exponential rate, as we would expect. We would expect this to just keep going. There we go. We would expect this just to keep going up like that in an exponential manner, reaching infinity when this reached 0. And we would expect as the energy gets smaller and smaller, by the time it got to infinity, it would reach 0. But there's two weird things that are happening here. Number one, it's reaching 0 well before infinity on the x-axis, and it's reaching on the not the x-axis, on the upper end of the wavelength well before infinity. And instead of going all the way to infinity with 0 wavelength, it gets to 0 well before that. It's something that they called the ultraviolet catastrophe. And it sounds like my cat wants to be part of the presentation here, so oh well. Sorry about that. Okay, so we have the ultraviolet catastrophe going on here. Why would this drop off to 0 when it should be going all the way to infinity? And why would this go to 0 well before it went to infinity? Well, that's where Max Planck came in. And as they were looking at this, they were saying, well, light's just continuous, and things that absorb light absorb it in a continuous spectrum. And he came along and said, no, I don't believe that's the case at all. I believe that it's quantized. That we have these things, in this case it was electrons, that are vibrating back and forth, and as they vibrate they absorb energy. But they don't absorb energy continuously, they do it in little packets. And we now know them, they call them photons. I'll tell you where they got the name here a little bit later. But in quanta of package, he never called them photons, he just called them quanta. And quanta is plural of quantum, I believe it is. So that's what Max Planck came up with. And when he came up with that, he said, okay, we have energy is equal to Planck's constant, he worked out Planck's constant times the frequency of that light. All right, so this is a very key equation that you need to know. And there is another one that we can derive from this fairly easily, because we always want the energy is the important thing about these quanta. What is the energy in that package of light? So we can derive another equation from this. So this is our first equation. We know from classical wave physics that the velocity of a wave is equal to its wavelength times its frequency. That and we're really talking about, since we're talking about light, let me get rid of this. We're talking about C. So we can rework this to find that the frequency is actually the wavelength. I'm sorry. Can't do my algebra. It's early in the morning. So let me get here. So the equation is actually C over lambda. So we can replace the F here, and we have E equals Planck's constant times C over lambda. That's our second equation. Okay, so that is basically Max Planck's contribution to quantum mechanics. Doesn't seem like a whole lot, but it turns out to be everything, because you're going to see this equation show up over and over again. And just to note that in 1900 is when Max Planck brought this out, and it was 1917 when Bohr presented the paper on his model of the atom. And so Bohr used the concept of quanta to build the orbital model of the atom. So this is really the beginning of everything. The next thing we're going to talk about is in 1905, Einstein did something called the photoelectric effect. Did it squeezed in it? Yay, photoelectric effect. All right, and this, again, using quanta discovered by, or hypothesized, I should say, by Max Planck. All right, so let's go talk about the photoelectric effect. All right. All right, this is a very simplified model of Einstein's photoelectric apparatus that he did. I'll draw a little better representation of what it actually looked like. But if you notice here, you have two metal plates. Basically, this is a capacitor, right? Two metal plates a distance apart from each other. The only dielectric in here, I believe, is either a vacuum or it's air, because you're shining light onto one. One of these is photosensitive. Photosensitive. All right. And what that means is when light shines on it, it will release electrons. All right. So what Einstein set up was a kind of a circuit. He would see if electrons would flow from one. He would set this up. This one, yeah, let's see here. This one would be positive. This one would be negative. Excuse me. And he would have a voltage source, so he could adjust the voltages, and he would create an electric field in here. And then he would shine a light on this plate, and it would release electrons. Now, because the electrons are negative, they would be attracted to the positive plate and they would all move in that direction. Now, the way he had this set up is that they're actually connected by a wire and the electrons would flow in that direction. Okay, so he would have an ammeter set up here to check out what the current was flowing through here, and then he would track the voltages. Okay, so if you understand that concept, let me draw what his apparatus actually looked like. Well, this is not an actual picture of his apparatus, but let's draw here. We come down here to a battery. It's plus on this side, negative on this side. And then attached to this is a variable resistor. And on this variable resistor, you can move it back and forth using the resistor to actually change the voltage. And then he had a voltmeter attached, so I could see what the voltage difference across these two plates was. And in here, I should have left a space. Oops. All right. In here, he had an ammeter to read the current. All right. So this is how this was isolated into its own environment. And then he would shine light on one of these plates, and then we would get this action going on. Okay, so what he did was he would take the voltage from high positive voltage and he would move it all the way down until it got to 0, and then he would reverse polarity until he had negative voltage. So when he reversed polarity, what that did was, oops, I don't think I did that right. There we go, I hit the wrong thing. Why is my eraser not working? There we go. Forget it. Okay, we'll just go with this. Instead of this being positive, it was negative. And instead of this being negative on this plate, I see what's happening. I figured it out, but that's okay. This would be positive. So we're shining light trying to take electrons off the positive plate. So what you get is, instead of an electric field going this way, you now get an electric field going this way, right? And that the electron, when it comes off, it's still attracted to this positive area, but when it comes off, it's it's got more energy, you know, it comes flying off, and eventually, as you increase the voltage, you increase the power of this electric field, and eventually this electron doesn't want to leave. It just wants to sit here on the plate. Okay. So when Einstein did this experiment, he charted, let me draw a chart here. He charted something that looks like this. Okay, he had high voltage up here. He had negative voltage over here, and this is where he reversed polarity, where voltage went from 0 to negative voltage. And what he found was rather interesting. Now, he used monochromatic light, which is basically another way of stating a laser. And he found that no matter what the positive voltage was, the intensity of the photoplate, I'm sorry, not the intensity, the current, the I is for current, not intensity, stayed the same. All right, it just, regardless of what his voltage was, it stayed the same. And then when he got to the negative side, as he increased the negativeness of the voltage, it dropped until it reached zero, and then there was no more current whatsoever. And he called this area here the cutoff voltage. Okay, so that's the voltage where the current cut off. Okay, so interesting things about this when you think about this. If you have a voltage that is really high, you would expect more electrons to be excited and moving. That's what current is, right? Moving electrons. So you put more energy in, you should increase the current. So you shouldn't see a straight line here. And this is what you would not expect to see. You would expect to see that as this voltage dropped off, that you would get a kind of a dotted line down to zero. And then maybe the current would flow in the other direction, right? So that's just not quite what they were experiencing. He did notice that when he increased the intensity of the light and decreased the voltage, he got the same effect. You would expect, because increased intensity means more energy, so he did get more electrons flowing, and that means a higher current. And he expected it to take longer because there's more energy in those electrons. He expected it to take longer to get to the cutoff. But what we found was it came to exactly the same point. No matter what that intensity was, there was actually extremely low intensity. You would still get a current flowing immediately, and it would still cut off at the same area. So this was very strange. Okay, finally, he noticed that if he increased the frequency, all right, he would get incremental. Increase the frequencies, not always would you see an increase in the current, but it would increase stepwise. And here you would see it drop off at different rates to a cutoff. All right, so what does all of that mean? It means that the intensity of the light does not equal higher current. It's not the intensity. What you're getting with higher intensity is maybe more electrons moving, but with the same energy. When you increase the frequency is when you change the frequency. I'm sorry, when you change the energy. You increase or decrease the energy with the frequency, not the intensity. Very strange. It's not intuitive to what you would expect to see. Okay, so let me kind of try to explain what's going on with this. All right, so Einstein was looking at Max Planck's equation. Remember this? E equals Planck's constant, Planck's constant times the frequency, and we can also write it as h times c over lambda, speed of light over frequency. All right, so Einstein was looking at this, and he said, you know, there is movement with electrons when we're trying to release them from a sheet of metal. there is a potential energy that we have to build up before we can move it, and then there's energy left over for kinetic energy for movement. So he's looking at this equation and he said, okay, I'm going to modify this a little bit. HF is the energy of the entire photon that's coming in. It was Einstein that called these quanta photons because he wanted to emphasize their particle nature. Yes, we are talking about frequency when we're talking about a particle. So it's got both wave and particle nature. So he's the one that called it photon, and we represent photons with that Greek symbol, the gamma. Okay. All right, so he said the entire energy of the photon that is absorbed by an electron is equal to a work function plus the energy of the let me see, what's the word? Well, it's the least amount of energy. It's not the fundamental frequency, but it's the least amount of the lowest frequency that it takes to move an electron off of the metal. Okay, so what's a work function? Well, the work function is itself. I'm sorry. I looked at my notes and got myself all messed up here. All right, sorry about that. Okay, so I was actually pretty close to this. Work function plus the kinetic energy to come off. You'll see this as EK max, the maximum kinetic energy that is left over after the work function releases the electron. I'll give you a demonstration of this. This is the lowest frequency needed to move that electron off of the metal. All right, so let me draw you a quick picture here. What I'm drawing here is the surface. Now this is just conceptual, okay? This is not what the surface of a metal actually looks like, but this is how we represent it. Because when you think about it, when we talk about potential energy, right, a lot of times we talk about, say, taking a ball and lifting it to a certain height, right? So we have mgh is the potential energy of lifting that ball against gravity. So we have the same thing with an electron. Now it's not, we call this a well here, but this is not, they're not really wells in the metal. This is just representing the energy it takes to get that electron to come off the metal. So it takes some energy to raise that electron. Now, if you don't have enough energy, it's not going to make it out. It's going to stay on the metal and not make it out. But to get to the point where it's just leaving the metal, that's our work function. Okay, that is just the frequency of light required to get it to that point. A lower frequency will not get it out. A higher frequency will actually give it more energy, and the electron will have some velocity from the leftover energy to move, to have movement, and that's where EK max comes in. Okay, so here's how we represent this equation. EK max is usually represented by that. This is not electron volts. Not electron, this is the charge of an electron. And this is voltage. Okay, so we can represent this as HF equals a work function plus E K max. And we can also represent this as HF naught plus EV. Okay, or you may see E in front of it. All right, so this is all there is to it, and this is what Einstein's experiment showed, was that it's the frequency of the light that causes the energy that it needs, because the electron will only absorb a certain energy, a certain quanta of energy, a packet. And this is what Niels Bohr took when he used it to create his model, that the electrons only absorb a certain quanta of energy. So that all of these, at the same time, all these people were working on basically the same idea, that light has particle properties. Now what's interesting is that the photoelectric effect, I'll write it here so that, is something that we use every day. It's a big, huge part of our lives, and we use it quite effectively. You know, one of the things that is something that I use almost every day, maybe not right now, but when we're actually in school, is the copy machine. The copy machine uses light energy to shine on a paper, and as much as that light that's reflected back in wavelengths based on the color of the ink and the shape of the ink and everything, hits a receptor on the photocopier, and using that wavelength of light, or that frequency of light, the electrons come off with some energy or no energy or whatever, and with that leftover energy, the photocopier knows what color and shape and everything is on that paper, and is able to use that to create a photocopy. Same thing with digital cameras. It's the same exact concept. Basically, a copier is just a really big digital camera. But I use digital cameras in my astrophotography, and it's the sensor on the camera. It's just taking the light that it receives and releasing electrons, and it's reading how the electrons come off of that metal. That's what the pixels on the sensor are, and what they're doing. It's a very, very amazing process that we can do. There's one more thing that I can think of right off the top of my head that we use, not everybody every day, but we see every day, is solar panels. We see them on traffic signs that have blinking lights and things like that, and we see them on house roofs and things. So it's the same concept. Light is hitting that and releasing electrons and creating an electric circuit. So all of that has to do with the photoelectric effect, and so it's something that's quite important. Okay, so let's see how to apply this photoelectric effect. And here's a sample problem. A photosensitive metal has a work function of 5.5 eV. So work function 5.5 electron volts. And this is where it can get kind of confusing. This is electron volts. It's not charge times voltage. This is a unit, not an equation. So you're going to have to keep that straight. All right, find the minimum frequency. That's what I was trying to think of before. Equals, we don't know, of light needed to free an electron from its surface. Well, what do? We have the equation E equals, I'm sorry, let me put it this way. Let me write it as our full representation of what we have. HF, the energy of the photon that is coming in, equal to the work function plus, again, I want to set this up exactly right. So work function, so instead of saying work function, let's write out what the work function is. HF naught, minimum frequency, plus EK max. Okay, so EK max is, let me get rid of that. It's not electron volts, it's charge times voltage. Okay, so we know the work function here, HF naught is equal to 5.5 electron volts. Now, to use it in this equation, it has to be in joules. So our conversion for that is 1.6 times 10 to the minus 19th, excuse me, joules per electron volt. And that gives us 8.8 times 10 to the minus 19th joules. Okay. Pardon me for a second. I'm trying to look at my notes here and remember what I'm doing. I'm looking at the wrong notes. That's why I'm getting all confused here. Okay, so yeah, okay, so I've got the right joules. Okay, so because the work function equals, I can figure out what the minimum frequency is from this, correct? And so it's 8.8 times 10 to the minus 19th joules, divided by 6.63 times 10 to the minus 34th joules seconds, which is Planck's constant, which gives me 1.3 times 10 to the 15th hertz. So this is the minimum frequency that I need to just get an electron up to the surface, right? Up, you know, and again, it's conceptual. It's just, now that electron is just touching just off that surface. It's just at that point where it's ready to leave. We technically, it's left the surface of the metal. It just has no kinetic energy in it. And that's 1.3 times 10 to the 15th hertz. Okay. So let me do another one here. Okay. So let's again, we've got a work function of 5.5 electron volts. Find the maximum kinetic energy if we have, now remember the other one was 1.3, the one we just figured out that just got you barely to the top. 1.3 times 10 to the minus 15th hertz. And so if we wanted to, we could just subtract 2.5 times 10 to the 15th from this, and we get 1.2 times 10 to the minus 15th. This is the first time I've thought of that, so I'm going to see if this actually works out, and if it doesn't, we'll try to figure out why. Okay, so we already saw how to convert that to 8.8 times 10 to the minus 19th joules. Okay, so that's how many joules that is. We've got a frequency here. So the total energy of the electron, remember energy of the electron is HF. And so that's 6.63 times 10 to the minus 34th times 2.5 times 10 to the 15th. And so our energy is 1.658 times 10 to the minus 18th joules. Now from our equation, HF equals HF naught plus EV, or we can just call this EK max, because this is what we're trying to figure out. We're trying to figure the maximum kinetic energy. So EK max equals minimum frequency minus, I'm sorry, boy, I really don't do minor details in math well. Okay, minus HF naught, which is just what I have up there. Okay, so I have, no, it doesn't come out that way. Sorry, this is not this. I was missing something there, so this is not right. So HF is, where did I figure out HF? Right up here. So HF 1 point, yeah, I was doing hertz, not joules. I don't know what was going through my mind. So anyway, sorry about that. Times 10 to the minus 18th joules minus 8.8 times 10 to the minus 19th joules, not hertz, but if I took 1.2 times 10 to the minus 15th hertz, I'm going to see if that comes up to the same energy using this equation in just a second. Okay, so and that's going to come out with 7.8 times 10 to the minus 19th joules. So this is the energy that it comes off with. Now, it's kinetic energy, and if you remember, kinetic energy can also be represented by this. So if you want to see what the velocity that it comes off with that energy, use this equation, and we know the mass of an electron is 9.110 times 10 to the minus 31 kilograms. And so we can just substitute this for that, put that in there, we can solve for the velocity. All right, now give me just a second. I'm going to see if 1.2 hertz, 1.2 times 10 to the minus 15th hertz equals 7.8 times 10 to the minus 19th. 1.2 to the minus 15 times 6.63 to the minus 34th equals, I came out with, whoops, sorry, pushed the wrong button, 7.96 times 10 to the minus 19 joules. They both round up to 8 times 10 to the minus 19th joules. Did I come up with that? No, I came up with minus 45. Okay, this method is, so this is minus 45, sorry. So no, can't just subtract the frequencies. That's not how it works. We're missing the quanta. The reason why I had a problem with this is I was thinking classical physics. I was thinking constant distribution. I wasn't thinking quanta when I did that. So, so this is the method that you need to use to answer these questions. Take those quanta into considerations. Okay. All right, so that is the photoelectric effect and how we can determine the velocity and the energy of a photon that's released from a metal plate. It also tells us that it's the frequency of the light, not the intensity of the light, that gives that energy to the photon. Okay, so let's move on. So we've got light and energy. Light has a particle nature to it. It's both particle and wave nature. Now, those of you that speak French, I apologize. I'm going to totally butcher de Broglie's name. He's French, so it's de Broglie, or however the French might pronounce that. I say de Broglie, which a lot of people do. But he came along and he thought in 1924, after all of these quanta and duality ideas came out, he decided he was going to come up with an idea that if light has particle nature, then why doesn't matter have a wave nature? And he came up with this, and of course, when he first came up with this, he was just like the laughing stock of the science community. It was totally ridiculous. And but then people started doing experiments, and it started to explain a lot of things that they saw. So he has the equation that the de Broglie wavelength, the wavelength of a particle, is equal to Planck's constant over its momentum. And if you remember, momentum is mass times velocity. Okay. So that is basically what he came up with, and subsequently he's been proven right that this is the case, that this is what happens. Okay, so let me do a problem here. Yeah, we're not going into a whole lot of explanation here, a lot of his experiments and things, because we're getting into the realm of calculus, which we don't do in IB. So just take it for granted that this is the equation, and you can apply it. All right, so we've got an electron that is accelerated from rest through a potential difference of 100 volts. What is its expected de Broglie wavelength? All right, so we've got several things that are going on here. First of all, we need to find out what its velocity is, so we can use this equation. We know the mass of an electron, but we know the energy that there's given, because it's given to us in volts, and we can figure out the wavelength. So we're going to be using the equation, and so basically that's going to be lambda equals E times the mass times the volume. Is that right? Did I do that right? Lambda equals mass times the volume. I'm looking at my notes again. And is that right? H. Yo, sorry. Holy moly. It has been a long thing. This presentation has not wanted to get produced. It's been one technical error after another, so I'm just a little bit off, so sorry about that. Okay, so we have the wavelength equals h over p, which is h over mv. So this is the one that we're going to use, because we know the mass of the electron, we're given the energy, so we can figure out its velocity. Okay, so how do we do that? Velocity, kinetic energy we'll figure out the kinetic energy first. Kinetic energy is the charge of an electron times the voltage that it's going through. So it's 1.6 times 10 to the minus 19th coulombs times 100 volts, and that gives us 1.6 times 10 to the minus 17th joules. Okay, so now that we have the kinetic energy equals 1/2 mv squared, and we can solve this to find the velocity is equal to the square root of 2 times the kinetic energy divided by the mass. Make sure I set that up right. Make sure I'm not making another mistake. Yeah, okay, so that looks good. So velocity equals the square root of 2 times 1.6 times 10 to the minus 17th divided by the mass of electron, 9.110 times 10 to the minus 31. Take the square root of that, and we get a velocity of 5.9 times 10 to the 6 meters per second. Now we can take this and substitute it in right there, and so the wavelength is equal to 6.63 times 10 to the minus 34th joule seconds, Planck's constant, times 9.110 times 10 to the minus 34th times 5.9 times 10 to the 6th, and that gives us a de Broglie wavelength of 1.2 times 10 to the minus 10th meters. And 10 to the minus 10th meters is basically an atom. That's an atomic radii. Atomic radius. That's basically the size of an atom. So the wave of the wave nature of an electron is the wavelength size of an electron. I'm sorry, of an atom. Okay, so that's kind of interesting. Such a tiny object has such a huge wavelength compared to its size. Thousands, millions. Let's see, an order of. I'm trying to think of diameter. It's large. It's a lot of zeros. Times the size of an electron is its wave nature. So if an electron has such a large wave nature, such a large size, we're particles too. We're just one great big particle, right? In a sense, we've got lots of little particles, but they all add up. So what kind do we exhibit wave nature as well? Well, let's take a look at that. Let me take a look at two things. I'm gonna talk about me. Me at going 35 miles per hour, which is actually 15.6 meters per second, and I weigh about 205 pounds. So let's see, that's my velocity. My mass is 205 pounds, which is about 93 kilograms. So let's also do me going at as fast as that electron was coming off of the what our last problem. It's wave nature. An electron that had that much energy was moving at that velocity. If I was moving at this velocity, which is pretty close to, it's about 0.2% of the speed of light, which is pretty fast. That's pretty fast. That's really moving. So let's see if I have any wave nature at these. So we're basically using lambda equals h over mv. So in my case, 6.63 times 10 to the minus 34th, 93 kilograms, times my velocity is 15.6 meters per second. And so my wavelength, my de Broglie wavelength is 4.57 times 10 to the minus 37th meters. I'm smaller than an electron. My wave nature is smaller than an electron. The wave that I'm putting out, the probability that I exist within this space is pretty certain, because I'm way bigger than that space. But the faster I go, the bigger my wave should be, right? The bigger my de Broglie wave should be. So let's see what it is. Lambda equals 6.63 times 10 to the minus 34th. I'm still 93 kilograms. Now, honestly, my mass would be bigger if I was going a significant portion of the speed of light. That's just the way it is. But we'll go with, it's still 93 kilograms. And I'm going 5.9 times 10 to the 6 meters per second. And so my wavelength is 1.21 times 10 to the minus 42. The reason why this is so much smaller is because we'll talk about this next time when we talk about Heisenberg's uncertainty principle, but I'm moving, and so it's harder to tell where I'm at. And so my wave function is way bigger, or I'm sorry, way smaller than this one, because it's harder to figure out. No, actually, I'm saying that backwards. My wave is smaller, so there's even more chance of, this is why you see me all the time. No matter what velocity I'm moving, you'll see me moving. You'll see where I'm at. You can see where I'm at because my wave function isn't very big at all. As a matter of fact, it's, I think mathematically, the term for this size of a wave function is zero. It's virtually zero. Even at an atomic level, this would be an atomic level to that one. Again, on much smaller. If an atom's order is minus 10th, if my wave function is on the order of minus 42 or even minus 37th, I mean, even an atom couldn't see me, couldn't see my wave function. It would just be too small. Okay, so next time we will move on and talk about some other ways that matter interacts with radiation, basically the quanta nature of matter, and there will be some intense equation derivations coming out of that. Good news is some of them you're not going to be expected to do. Other ones you are going to be expected to know, but it's algebra, right? It's not, sorry for those of you that really want it to be calculus, it's not. It's algebra 2, maybe even just algebra 1. And the one thing you can look in the book, there is one that there is a calculus derivation for, and they put it in a big box. You're not expected to know how to do this in IB, so they're just showing you how they derived it, but you're just supposed to know the end result of it. So we'll talk about that then. Work on the worksheet up until, let's see, work your worksheet through question number 7 is all. We just went through question number 7. And then we'll talk about what you need to know for 8 through 21 next time. Let's see you then.